So hopefully, I hope everyone had a good weekend and is ready to get back at it. So I was didn't get around to sending out a weekly announcement. I try to do. I'm going to do that after class, just so we have it written. I think the big thing is this week there are going to be quizzes in the labs that are going to be talking about largely the trig integration, with some leftover integration by parts, I think, today, for the people that have Monday lab. But let's talk about it. So as a reminder of what we were doing last time, we were evaluating integrals that look like this. So the integral of sine cubed x cosine to the 7x dx. So integrals that involve just trig functions or some powers of trig functions. If you have looked into homework, there are some variations that aren't just power of sine, power of cosine, but the way that we deal with these is a little more flexible and can handle some different situations that are hinted at in the homework. The big idea is, given this integral, we really want to get to a place where we're doing u substitution. And there are two choices for how that could work, because we can't do it right away. So the question is, do we want to get to u is sine and du is cosine, or do we want to get to u is cosine and du dx? And du is negative sine dx. So in class, we laid out kind of step-by-step procedure, but this is what it really boils down to. Which of these do we think we're going to be able to do? And what's a little different from the way that it seems like we've used u substitution, the big thing is, which du do we think we're going to be able to get? Because if this is going to work, we need to have this single du, and then everything else in terms of the other trig function. And the way that we, I guess the other half is, this is the u substitution we're going for, and the way that we get just one trig function and then everything else in terms of the other trig function is, we have these trig identities. The two main ones that kind of go with this section is that sine squared is 1 minus cosine squared, or cosine squared is 1 minus sine squared. So we're able to turn sines into cosines and vice versa. So these are the tools that are going to end up getting used. Then the question is, in this case, do we want to get a single sine and the rest be cosines, or do we want a bunch of sines and a single cosine? Do people have an idea of which u substitution should we aim for? Do we want a single cosine or a single sine?
The top one.
So this one. Why?
Plus, there's not a negative sign or problem.
Right, so that's one thing that definitely makes this easier to use. Although in that case, as we've seen in a lot of use substitution, if you're off by just a minus sign, you can sort of move it around. So that's one reason why, given the option, the top might be easier to deal with, but that's not a kind of a deal breaker as far as making this one work. If we look in the not the solutions, but the strategy that we laid out last time, the big thing that we're looking for is if one of the powers is odd, then that means you can take one of those and isolate it as your du, and the even power that you have left, you can turn into the other trig function using these guys. Which in fact doesn't, well, in our case, both of these are odd. So in this problem, you could end up using either one of these. You could take one of the signs and turn the rest into cosines, or take one of the cosines and turn the rest into sines. So this way you could go with either option. And so in this case, it's really all about, well, which one do you see? If you typically try to make this one work, then you might just jump into this. For me, when I'm looking at this and thinking about what might the work look like, what I think is the easiest way to move forward is leave the cosines alone and break off one sine. So I think why I think this will turn out to be easier is when we're thinking about how much trig identity stuff do we have to do, what we really have is there's this single sine squared in there, and that we're going to use this trig identity, but then we get to where we want to. A bunch of cosines, a single sine, we're set up for the u substitution. If you think about doing it the other way, peeling off one cosine, what you really get is you get a cosine squared, another cosine squared, another cosine squared, and then the single cosine. So if you try to turn your cosines into sines, because there are more cosines, you're going to have to use this a bunch, and it gives you a pretty big looking thing, which isn't significantly harder to deal with, but you have to multiply out a lot more of your binomials, and there's more places to mess up, and we'd rather avoid it. So this way kind of gets us to where we want to go in the cleanest possible procedure. Before we actually do this, are there any of these sort of preliminary decisions or considerations that people would like some elaboration of, or just have me talk about again? And this me talking, maybe you're thinking, yeah, get to the point. But these kind of thoughts and looking at it and weighing what's the best way to approach this, that is something that is kind of part of this techniques of integration topic. It's not just being able to execute something, but identifying I have a bunch of tools, what is the right tool to use in this case? But having identified, we're going to use this trig identity, and then we're going to use this u substitution, then we can attack this. said we're leaving the cosine alone. This sine is becoming 1 minus cosine. This sine we're leaving alone. And now we can do the u substitution. In one example last time, there was a question about what's the order you deal with things, and it's really up to you. You can multiply this out first and then substitute. I'm going to just substitute, and then once it's all a bunch of u's, multiply it out, because polynomials look easier to multiply. So what do we say? This is what we're doing. Moving the negative sign around like we need to, negative du is sine x dx. So that sine x dx is what we actually have, and we're introducing this extra minus sign. So cosine to the 7th is now u to the 7th. 1 minus cosine squared is now 1 minus u squared. This sine x dx gets a du. And then there's a negative sign we have to put somewhere. I'll just multiply it in front here. Just to put it somewhere. And now, as really all of these problems go, after you do the u substitution, it's a bunch of powers of u, and we have to multiply it out, but we're on the right track. So multiplying things out, those two and the minus side become the integral of u to the 9th. Add the exponents. Negative u to the 7th times that 1 is minus u to the 7th. And then the power rule, u to the 10th over 10 minus u to the 8th over 8. And then u was, we were doing this one, u is cosine. So we make it to cosine to the 8th, or sorry, cosine to the 10th over 10 minus cosine to the 8th over 8 plus c. Questions about this problem? So especially once we get here and beyond, it's a lot of similar moves in a lot of these problems, but really deciding which combination of substitution and identities are we going to use is where really most of the thought and effort is going to go. So let me do one more sine cosine example to remind us that this isn't the only way that things can go. Using the substitution and these Pythagorean identities is, I would say, by far the most common way, but there are other situations that we need to watch out for. So let me do this one. Let's do the integral of sine squared times cosine squared dx. So in this example, sine squared times cosine squared, they're, even as I was writing it, as I mentally thought sine squared, cosine squared, oh, that's 1. No, that's if they're added together. Here they're multiplied, so they're just 4 trig functions multiplied together. And this is the situation where we really have to do something else. The reason why this combination works in a lot of cases is, well, if there's an odd power, then that lets you peel off one and change the rest to the other trig function. In this case, it doesn't work. We have an even number of both, and we can't get a single sine or a single cosine set off to the side. So this was that other case that is the most annoying because it just doesn't, it takes something basically completely different than these. So the identities that are relevant here, there are three, and they can get used in different combinations. So the three most relevant are that sine squared is 1/2 1 minus cosine 2x. Cosine squared is 1/2 1 plus cosine 2x. And then there's another one, sine times cosine is 1/2 sine of 2x. So in this problem, there are really two ways that we can do this. One way is, and this isn't the one I I'll do one way and then kind of indicate another way that we could do it. So kind of the way that's staring us in the face is each of these sines and cosines we can turn into these other expressions here. So this is the integral of, instead of sine squared, 1/2 1 minus cosine 2x. And then 1/2 1 plus cosine 2x. And now we'll multiply these out. The numbers 1/2 multiply to get us a 4th. What's nice about this multiplication, it's a sum and a difference. So if you do those two and those two, they completely cancel. So what we get is 1 minus cosine squared of 2x. In these two, we're multiplying cosine by itself, or cosine 2x by itself twice. And that's what gives us the squared. And then close the x. And then let me multiply this out. So the 1/4, and then minus 1/4 cosine squared of 2x. So this is the new integral that we have to deal with. Does anyone have an idea of what we can do?
Couldn't you have taken the 1/4 out of the integral and then 1 minus cosine squared 2x would be sine squared 2x?
Yes, so that's one thing you can do. And actually, there are, in this problem, I think there are like 3 different ways you can go through this. So one thing you can do is, if you look at this part right here, 1 minus cosine 2x, that is 1 minus cosine. The fact that it's 2x on the inside doesn't matter so much. Well, you have to know that it's there, but this really says sine squared of whatever you want is 1 minus cosine squared of whatever that thing was. So one thing that you can do is you can turn this into sine squared of 2x. So that's one thing we can do. Even if you had sine squared of 2x, we would still have to figure something out, but that's a direction that you can go. The other thing that we want to notice here, the exit strategy here is we look at this and say, okay, we have cosine squared of 2x. And this identity tells us what to do with cosine squareds. And again, the fact that it's cosine squared of 2x, so we have to recognize that there's a 2x. But from the perspective of the trig identity, it's not so important. What this says is cosine squared of whatever is in here is 1/2 times 1 plus cosine of 2 times whatever that was. And even if that thing is itself a 2x, then that's fine. Just the 2x that's in here goes in place of this x here, and then there's an additional 2 that's put on top of it. So this is 1/4 minus 1/4, and this cosine squared is all of this stuff. So there's the 1/2, 1 plus cosine, but now we're saying whatever was inside your cosine squared, we're multiplying it by 2. So here this becomes cosine of 4x. And that one closes and that one closes. So using that blue trig identity, we can turn this cosine squared into some stuff with a regular cosine with a bigger constant in front. Okay. Clarifications about just that particular step, the sort of algebra part. So then the next question is, great, we've used these trig identities, and where do we go from here? And while this is a big mess, and you'll have to be careful about multiplying things together, the thing that we can notice is we at least don't have any powers of cosine anymore. Like it's just cosine. And if we have to integrate with an extra constant inside, that's something that we can do. That we have to account for that constant somehow, but it doesn't make the integration substantially more difficult. So if we multiply this all out, and now this step isn't hard, but there is a lot. So let's see. We're going to get the 1/4. This is just on its own. Then these two get multiplied together, and then 1 plus cosine to the 4x. So there's the initial 1/4. Then there's the 1/8. 1 plus cosine of 4x. And then we can multiply this out. And this gives us an 1/8. Combine that with a 1/4 to get an 1/8 minus 1/8 cosine of 4x dx. And once we're here, this is a place where we don't need any trig identities. We can integrate this. This guy's a constant. So that gets a new variable. That becomes 1/8 times x. This cosine, or the second term here, the 1/8 sticks around, cosine integrates to become sine, and the 4x gives us an extra dividing by 4 factor to account for the extra 4 that's inside. So the 1/8 is still there. Cosine becomes sine, 4x stays, divide by a 4 plus c. And now if we want to clean this up, we can get an 8x minus 1/32 sine of 4x plus c. On parts of this process that I can say more about. Right. So before totally moving on, let me address a little that there's more than one way through this. So what if, and I think I won't go all the way through here, but AJ said, in this case, you could turn this into sine instead. So this is also equal to the integral of 1/4 sine squared of 2x dx. So that's another move you can make. And if you get here, you really have to get into the same, where you make a really similar move, just that you're in a different position, because you have this sine squared, that power you can't do anything with. So now you have to use this trig identity. And if you replace that sine squared with this 1/2 1 minus cosine 2x, then what we get, the 1/4 is there, 1 minus cosine, and the same deal we had before, because we started with 2x in here, we double it to get 4x. No, and if we're, okay, right. I was thinking we need to get the same thing. So there's the 1/4 there is to start with, but then there's a 1/2 that shows up, and that's where these 1/8 come from. And so multiplying this out, you can really, you get right here, and you get the same answer. So if you decided to make this move, there's a little less stuff, but you get to the same place. As another way, just to really show you that there's more than one way to do this, and they can be just as correct. So this, at the very beginning, another way of doing it is saying, well, if you have two things multiplied together, then I can turn that into a single sign there. So at the very beginning, you can say, let's write this as sine times cosine, all squared, squaring the whole thing instead of individually. And then you have this trig identity. And so now this is 1/2 sine of 2x, all squared, which is exactly the same as this one up here. And then they all get finished the same way. So the point of this, sort of choose your own adventure thing is, one, there's more than one way. If you find some sort of thought process that seems to work for you, run with it as long as it's correct. The other thing is, from a sort of philosophical point of view, the word creativity is maybe not often associated with mathematics, but this is kind of creative. There are multiple ways of putting things together that you're kind of within the rules of how things are allowed to get put together, but there are a bunch of ways to do it. And it's, like building Legos. There are certain ways Legos can go together, but within the ways that you're allowed to put things together, there's a lot of ways to do it. And it's, there's some fun in putting this together if you're up for finding it. So this is all about sine and cosine. But this gives us a pretty good template for maybe there are other combinations of trig functions that can have a similar process. Not exactly the same, because there's sine and cosine work pretty well together. But there can be other combinations of trig functions that let us use this trig identity U substitution 1-2 punch. And so there's a similar strategy. Good. For integrals that look like an integral of tangent to some power times secant to some power. So if this is the kind of integral we're looking at, what we really need to identify first are, well, let's lay out what are the identities and what are the U substitution combinations that work. So we're recalling these identities. And again, these will be given to you when necessary. Certainly on exams and on quizzes, I might say, here, use this identity to do this problem. So the identities are that tangent squared is secant squared minus 1. So this lets you turn tangents into secants. And then moving the 1 around, we get secant squared is tangent squared plus 1. And then if we think about the U substitution, the U du combinations, there are 2 pairs with tangent and secant all over the place. So the first one is that if U is tangent, then its derivative, the derivative of tangent, is secant squared. Or the other option is that if U is secant, then what's the derivative of secant? The derivative in this case is secant x tangent x dx. So right here, I think this u du pairs lets us see that this situation is going to be more complicated. Because with sine and cosine, it was if you get one cosine and a bunch of sines, you're good, and vice versa. In this case, what you need to do is if you get two secants and a bunch of tangents, then you're good. Or if you get one of each off to the side and then a bunch of other secants, then you can do the u substitution. So we have to be a little more careful with what are we setting aside as our du to set ourselves up for the u substitution. So let's try one of these. Let's take the integral of tangent squared x secant to the fourth x. So the question is, do we think we can get two secants and a bunch of tangents, or can we get one of each and then a bunch of other secants? Does it seem like one of those is a better bet than the other? So if we're not sure, we can try them out. I'm holding the red marker, so what it means I'm going to write next is not going to be the thing that works. But if you try to go for this one, like there are secants and tangents there, so maybe you think, let's just take one of each. We can rewrite this so it's not a wrong thing. Like this integral is equal to the first integral. So, right, instead of 2 tangents and 4 secants, we have 1 and 3, and then tangent secant, or secant tangent, I guess, off to the side. So if this is the move you make, then what you want is everything else needs to be secant, but with this lone tangent here, the trig identity, which would let us move things around, doesn't work because we need 2 tangents, or an even number more generally, because then we could change them all 2 at a time. So this doesn't work. On the other hand, if we break this apart, so there's 2 secants off to the side, then we have tangent squared x, 2 of the secants, and then the 2 secants that are going to be put on hold for our du. If this is the move that we make, then we want everything else to be tangents. So the thing is this secant squared, and that's what this trig identity lets us do. So in this case, it ends up working. So once we've identified this u-du pair and a trig identity that lets us do it, it feels in a lot of ways similar to the other problems. Make the substitution, tangent squared, secant is tangent squared plus 1. This secant squared we're not doing anything with. And now do this u substitution. So this is the integral of u squared plus 1, secant squared x becomes du. Now multiply, power rule, substitute back. So multiply u to the 4th and then u squared, power rule, u to the 5th over 5 plus u cubed over 3. And now we get to substitute back in. And u was tangent. So we get tangent to the 5th over 5 plus tangent cubed over 3 plus c. Questions or comments or concerns about this? Either as these go, the actual execution, the algebra u substitution steps, or some of this discussion why this was the way we ended up going. So let's make sure there are no questions. So let's do an example, which, because we want to seal examples, is going to be where this is the, this is the case that works better. So let's say the integral of tangent to the 5th x secant x dx. So I gave away the ending, it's going to be this u substitution, but we want to think, what is it about this one which is not happening in this case? Well, the sort of obvious thing is we don't have two secants, so we definitely can't do that. But also, if we set ourselves up to, by isolating this secant tangent, we can see what's going to happen. So there's 4 tangents now, and then secant tangent dx. And what we can see happening here is we have those 4 tangents. We want everything to be secant, but because there's an even number of secants here, we can turn them into this 2 at a time and convert all those tangents into a bigger polynomial, but something that only has secant in it. So skipping a step, this is tangent squared, tangent squared. Each of those gets turned into secant, or secant squared minus 1, second secant squared minus 1, the secant tangent du that we set off to the side, and now we have this second u substitution set up. The first 2 factors are going to become a u's, and the second part is exactly what we needed for the du. So then we can do this. Integral of u squared minus 1, u squared minus 1 du. This multiplication is a little, it has more going on. We're not just distributing, but still binomials. So this thing becomes those 2 u to the 4th. Middle outside is negative 2u squared. And then the last 2 gives us positive 1. And now power rule, u to the 5th over 5 minus 2u cubed over 3 plus u. And then we had secant tangent, we did secant, that was our u. So now this becomes a big polynomial with only secants in it. Give our summary. So secant to the 5th x minus 2/3 secant cubed x plus secant plus c. So these two examples are really kind of prototypes for the general situation where this is able to work. So what is happening in these two that lets us actually work through this machinery in each case? So I'll lay out this general strategy like I did for sine and cosine. So for the integral of tangent, I'll use the right letter, to the m of x, secant to the n of x dx. So case one, if n, the power of secant, is even, which is what we had happen in this case and is not what happened in the second case. Then what we can do is isolate a secant squared x. If we have an even number of secants and we take 2 away, we get another smaller even number. Then we can convert the remaining secants to tangents. And since there's an even number of secants, we can do it using this trig identity however many times we need to. And then use the substitution where u is tangent and du is secant squared, the secant squared that we isolated from the very beginning. So if your power of secant is even, then we'll always be able to do it. And it doesn't matter how many tangents you have. That just, if this 2 was a 20, that would have just changed this power, but wouldn't have affected it. So the second case is if m is odd, then we're going to be in this other case here. So then we isolate a secant tangent, and I should say here, and if n is greater than 0. So you need to have some secants in here, otherwise things go a little bit differently. Then get a secant tangent like we did in that second example. And then the kind of usual rest of the process, convert the remaining tangents to secants, and then use the substitution where u is the secant and du is the secant tangent that we had isolated from the very beginning. So one thing which we'll notice, and I won't write any more stuff down, this doesn't cover everything. If you have an even number of secants, you're good. If you have an odd number of tangents, you're good. But what if you have an even number of tangents and an odd numbers of secants? That is just a more complicated case that doesn't fit into these. And we'll do a couple examples of those just to see why we're not going to go too far in that direction, but we want to be aware at least of how it gets complicated fast. Okay, we'll pick up with this on Wednesday. And that should probably be the last trig identity day before we move on. All right, see you later.